The application layer. Now, obviously, there are many applications, and if you understand them, you can do a much better job of analyzing them. We will be covering three applications: DNS, HTTP, and HTTPS. TCP dump does understand some applications, but BPF is a layer 4 tool. You can use TCP and UDP and make it so that the byte offset goes inside the data, which will be the application header, but this is not always effective. Applications always use ports, so you can use BPF and TCP dump to extract the data from a port and then use a layer 5 tool like T-Shark to do the analysis on the application. Let's start with DNS. How does DNS work? When a client queries the DNS server, if that DNS server is authoritative, it will answer. If not, you will be referred to a root server. The root servers only know about the top level name servers like .com. After that, you will be referred to a top level name server, and when you query it, the top level name server gives you the IP address of the domain name server, and then the domain name server will answer your query. Almost all DNS records can be used for malicious behavior like C2 and exfiltration, but the type of records that you want to focus on are TXT records and null records. Here's a DNS response message, which you shouldn't see that often and can be used for malicious activity. It is common to have two DNS servers, one as a primary and the other one as a secondary. The way the secondary gets the information is by doing a full zone transfer. It is critical that the secondary is the only machine that can perform this task. No one else should be able to do a full zone transfer against your primary DNS server. DOT allows for DNS information to be encrypted over TLS using port 853. This port should be blocked so that DOT is not used in your organization and you can monitor the traffic. Another method that DNS information is being encrypted is by being sent over HTTPS. Most browsers nowadays have this enabled by default, and it's important to disable it to be able to analyze your DNS traffic. Let's do some DNS demos. So let's start the DNS demo with a full zone transfer. So here's a query for a full zone transfer, and let's see what you get in an answer. In the answer, you'll get everything. So this is very dangerous if other machines are allowed to do full zone transfer against your DNS server, because now the adversaries have all the information that they require. So only the secondary DNS server should be able to do this. Now let's take a look at some normal DNS traffic. So interestingly enough, if you take a look right inside the flags, the first thing that you'll see is that it's a response, right? And if we apply this as filter, if we put 1, right, it says the message is a response. And if it says 0, if the response field, it's a 0, it's a query. So technically speaking, a DNS message is either a response or it's not a response. So that's quite interesting. Now here we don't have it. Let me go to this other PCAP file. I want to show you this in the response. Inside the response, at the end, there is the reply code, right? Now, the reply code normally would be 0 for no errors. And if you get 3 would be for NX domains, right? No such name. Now, if you go back to the original PCAP file, let's now go down inside the query. Now, inside the query, everything is very self-explanatory. As you can see, we have the name and we have the type, right? Now, let me show you something interesting about the name field, which you have to take a look at inside the raw format. So let's take a look at the raw format of the name field. As you can see, there is O3, you have the W's, and then on the dots you have 1 O, and then forward on the dots you have O3, and at the very end you have 00. Why is that? Well, technically speaking, between all of these there is a dot, right? So dot in the beginning, after the W there's a dot, after Google Analytics there's a dot, and after the com is a dot. each dot does not represent its own value, but it represents the number of characters coming after that. So O3 is going to be 3 characters for 3 W's. Then you have one O 16 characters in decimal value. And again, another O3 for comma being 3. And at the very end, nothing comes after the dot, so the value is 0. And then you have the type A. So the only thing to know about is that in the name field, the dots themselves do not exist. Now, I wanted to show you 2 more examples of DNS. The first one being iodine. As you can see, this is a DNS tunnel that adversaries will most likely try to use, which uses the null type. And as you can see inside the name, you will see all the information that is going to be used for the tunnel. Now, the next example is that I found this Medium post by this person, and here he used DNSCat for his example. And DNSCat, as you can see, it uses MX and TXT records and some CNAME records for doing the C2 channel. So as you can see, DNS can be used for C2 exfiltration and so on and so forth in various different ways. And having the logs to be able to analyze and see these is very important. HTTP. HTTP is based on requests and responses, and each of these have several fields. Let's take a look at them. In the methods, you will most likely are going to be seeing get and post. Delete and put are generally referred to as dangerous methods because they can change the content. Now, these fields can be used to inject, or malware could use random values or any type of weird value to hide itself. So it is important to look out for those. The way we would analyze the status codes are by monitoring them in a time range. Normally, you will see a steady line for the number of occurrences for these status codes. Now, if in a weekend the number increases by large amounts, that is the indication of weird activity in your network and should be investigated. Now, I wanted to dedicate a specific slide for the user agent. The reason is because the user agent is full of information and it can almost never lie. What information exactly? Well, if you go and take a look exactly, you will see that the user agents are generally very similar. And what they show you is, for example, the Windows version. They will show you the browser that is being used and other types of information as well. Now, these user agents can actually be whitelisted in a non-traditional way. What do I mean about that? What I mean is that you cannot make like a specific list and then do a diff against that. That wouldn't work. But the way you would do it is that you would make a list of known goods. Like for example, this is a Windows 10 machine. And you can take a look and see how a Windows 7 or 8 would look like with different browsers, right? And what you would do is that you would run the user agents in your organization against this list by just normally looking at them, not doing an exact diff because the numbers and the versions can vary. And by doing that, you may start to see weird user agents. You may see a user agent that is simply just SQL map. You might see some that might not have the correct capitalization. You may see random user agents, and with that, you can find out that you're actually being attacked by those hosts. Let's do a few HTTP demos. Okay, so if you're wondering how a HTTP header looks like, here are a few examples. So here we have some requests that, as you can see, with different types of packets or different types of requests, the header will change slightly. And let me show you a few responses. Response. And here they are. So for the status codes, we would use something like a sim to be able to do timeline analysis. But for the other fields, you can easily use T-Shark to extract them and find all the events of interest. So for example, if I use T-sharp, right, to read on this all PCAP files that I merged, if I extract the field, now, how would you know what field to extract? So normally, if you don't know the name of that field, you can easily do something like this, apply as filter, and take a look at that, and then apply that. Or if you want another field, like, let's say, it should be in the request. So give me a second, the request. Yes, so user agent, for the user agent, you would take a look, exactly. This is how user agents look. And you can just paste it like that, and bam. Now, normally it would show the other packets as blank lines. So you can do is sort with the unique command, and that should make it even better. And now, as you can see, you will see the user agents that are being used in your organization. So for example, some shell shock being injected and some other good stuff. So, and you can do this for almost all application fields. So it's a very effective way of extracting fields and finding events of interest. HTTPS. Before we start with HTTPS, I would like to first mention Let's Encrypt, which is a free way of deploying websites with TLS. Now, why am I mentioning this? The reason is because everyone now can use Let's Encrypt to deploy a website with TLS, and this can include adversaries as well. TLS will encrypt the HTTP data, and the way it does it is that it sends hello messages and it will exchange certificates and keys. Now, one might ask that, okay, now that the headers are encrypted, how am I supposed to analyze the data? Well, actually, the certificate itself has several fields that you can analyze, and it will help us in finding the adversaries. So here are a set of good certificates. You can definitely extract more fields out of it. And another thing is that the timestamps. So for example, good certificates are generally older, and well, the company associated with the certificate is actually going to be older rather than being a very new company. And here are how evil certificates will look like. So originally these slides didn't exist, and I would jump right into the IDSs, Zeek and Suricata. But then I remembered all the misconceptions and myths surrounding IDSs, and so I decided to make these few introductory slides. A traditional IDS has a set of rules it checks packets against. If they match, it will alert. But all alerts are not created equal. No, an alert can be four things. A true positive, which means that bad exists, and we got an alert for that. False positive means that bad doesn't exist, but we got an alert for that. True negative means that bad exists, but we didn't alert for that. False negative means that bad doesn't exist, and we didn't get an alert for that. Now, let's focus on the false positive. Bad doesn't exist, but we got an alert, meaning that even if your organization is highly secure, which is unlikely, you should still get alerts. In conclusion, you cannot deploy an IDS and not get any alerts. A lot of people may want to start deploying IDSs, and when they ask vendors, what they might tell them is that, hey, we have an alternative tool which is called an IPS. What it does is that it can prevent you from all the attacks and keep you secure. And if you want detection, you can put it in IDS mode. And a lot of people might think that, oh, we pay for one tool and we get two capabilities. False. An IPS must drop packets, meaning that it must have 0% false positive. If it has false positives, it is dropping your customers' packets, which, let's just say, it is not nice. Another issue you will encounter is that you will have far less rules to work with. So it is important to understand that an IPS cannot replace an IDS.